Okay, I think we're gonna get started here. Let the last few people trickle in. So, welcome back. This is lecture 7. Today we're going to be discussing decision trees, and I hope everybody got the memo about Tuesday's lecture being cancelled. No one came in when they were supposed to, and in case people are curious of why Tuesday's lecture was cancelled, I was in Hawaii for about 18 hours, which was not enough time to be in Hawaii, but that's where I was. I was at the Association for the Advancement of Artificial Intelligence. So I was giving a tutorial on my research. I talked a little bit about in the first lecture on machine learning with graph structured data. So the conference is still going on. This is one of the big conferences in machine learning, but I came back here because I couldn't miss 2 lectures. And yes, and that's a good segue to the fact that for those of you who are very interested in machine learning or want to maybe get a head start on what's going to be involved in the final project, it's good to have knowledge of kind of what's happening and the state of the art in machine learning. So one of the places where this happens is at this AAAI conference, as it's known. It's the Association for the Advancement of Artificial Intelligence. This was historically one of the biggest conferences in AI, still one of the really big ones. And an interesting thing about machine learning and about computer science in general is that unlike other academic fields where most things are published in journals, in machine learning we almost exclusively publish and present our work in conferences. So in like biology, you would publish things in, say, Bioinformatics Journal or like Cell or Nature, whereas in machine learning, almost all of the kind of top tier work from the best labs is published in conferences. So this is a good thing to know, both if you're interested in kind of looking into what's happening at the state of the art, this year in machine learning, and also because in the final project we're going to ask you to choose a recent paper that was published in one of these top conferences and to do some analysis on it. So just to give you a bit of background, this is not a super authoritative list. There's probably people out there who will disagree with me and say, hey, you left out my favorite conference. But if you're looking at, where do you want to look if you want to find, some of the most exciting work in machine learning? For general machine learning, there's 3 really big conferences. So there's one called ICML, the International Conference on Machine Learning. There's a conference called NeurIPS, whose acronym changed recently for reasons maybe some people can imagine. And then there's also AAAI, which is the one I just mentioned. So these are kind of big general conferences. AAAI was huge in the 80s and is kind of the birthplace of what people call these days good old-fashioned AI, which is more what you'd see in 424 than this course. And then in recent years, NeurIPS in particular has kind of taken over as the big dominant conference, and that was actually in Montreal in December. Some other conferences that are still equally as good but a bit more specialized include what are often called the ACL STAR. So these are all natural language processing conferences. It's actually the same organization that runs all of them. So that's if you're interested in language methods, the kind of things you saw a lot in Comp 550 if you took that course. And then there's CVPR for vision. There's some other conferences that are a bit more statistical and a bit more learning theory, so very theoretical. And there's a conference called ICLR, ICLR, that is kind of a new up-and-comer that's all about deep learning. So just in case you're curious, you want to see what's happening in the world of machine learning, these are the best places to look. And I think I mentioned in maybe the first lecture, but I'll reiterate that the tutorials that are given at these things, oftentimes slides will be posted, and those can be really great ways. So these tutorials are usually aimed at kind of people who are familiar with the basics of machine learning, so like where you should be after this course, and they're nice broad overviews of particular areas. So highly recommend all of that, and we will revisit this when we get closer to the final project and as you try to figure out what kind of paper you want to do analysis and reproductions on for the final project. But I think probably the thing on most people's mind is Mini Project 1. since it's due tonight at 11:59 p.m. It is stated in the syllabus, but I'll reiterate that late assignments are accepted. You just get a 20% penalty, and then you have 5 days. But I will say, like, maybe you're thinking to yourself, like, oh, I got, like, most of it done, but I haven't done anything super cool. Maybe I should take that late penalty. I would recommend, like, if you've got everything done, keep it simple. Don't go crazy overboard. Hand in the assignment if you have kind of all the requirements finished. And related to that, I think, in terms of advice I'll give at this point, if people are stressing about, say, trying to get their features working well, the new features they're supposed to be developing, again, keep it simple. You don't need to do anything super crazy. Think about just simple transformations of the variables we give you. Try out simple things before you go overboard with a lot of interesting text processing, which is fun, and it's going to be relevant to the next mini project. But again, when we're in the final day and the final hours here, there's no need to go totally crazy using all these off-the-shelf natural language processing toolkits. It's a very fun and useful thing to do, but you can do very well in this assignment just by keeping things very simple. So that is my one piece of advice there. I will quickly answer questions if people have them about the mini project, yes. These slides? Yes, these, oh, sorry, I forgot to. I was flying, so I didn't get the slides up. I apologize. Oh, good point. It will be posted right after lecture. I'm sorry, yes. And I apologize if I'm a little jet-lagged. I have been on a plane for the last 24 hours. So. Yes. Yes, so there's a discussion board about this. So the improvement is, it really should be per feature. We're not going to be really harsh, if you're like, oh, it's slightly below that. Like, you will lose a little bit of points, but we're not, again, we really don't try to be adversarial in the grading. Each of your features independently should give, at least a 0.005 improvement on MSE, really. And that means that kind of comparing against the baseline, when you add your feature, you get 0.005 improvement. And then again, comparing against the baseline, if you add your other feature, you get 0.005 improvement. It doesn't mean that feature 2 needs to give another 0.005 improvement after you've already added your first feature, if that makes sense. Just means, so what I mean by that is some people were concerned about, so my features together give 0.005 improvement, but new feature 2 doesn't give an improvement of 0.0005 after I've already added new feature 1. That's okay. As long as together they give 0.005, and if you just added 1, they give you 0.005, you'll be okay. Again, we're not, like, that 0.005 magic number just comes from, like, that's a meaningful improvement. Less than that is probably just noise. Yes, so this is something that's mentioned in the write-up portion. And again, we're not expecting you to go overboard there, and I think it's interesting because I collected this data. But I just am, expecting you to maybe comment on, do users on Reddit, who are, again, everything's pseudo-anonymous, we're not looking at any of their usernames, but do they have a reasonable expectation of privacy? What are the sorts of things when you're working with this kind of data that you would, or would you want to release the usernames with such a data set? Would you not? Like, just some, evidence that you're engaging with the fact that this is real world data, this is stuff that real people actually wrote, and thinking about maybe why I didn't give you guys all the details about these comments. And again, I should say that this Reddit data set is actually just publicly available for anybody to use. I didn't do anything special to get this, but it's still worthwhile to think about because not all data sets are kind of as public and as pseudo-anonymous as Reddit. And again, I apologize about not posting the slides. I meant to do that with Airplane Wi-Fi. Okay, so now getting into the lecture. Oh, yes. No, but we So this is similar to the way that conference reviewing works in machine learning. You're welcome to include appendices, but we probably won't read them. So if you want to say, because it's just frankly, that's the point of having a page limit, is because we have, limited, if everybody wrote 20-page reports, it would be awesome, but it would be an endless amount of grading. So the way you should use appendices is you should use them to support, like you might say in the text, we did a number of experiments comparing this and that, and we found that in these settings it gave a significant improvement of about 25%, and then in parentheses, like, see the appendix for detailed plots, right? And we'll probably glance in there, but the appendix shouldn't have, like, standalone information. It should just be basically, like, supporting things that you're talking about in the main text. Yes, and so in terms of, again, we leave things pretty, we don't give you, this assignment, we're giving you the most instructions on the structure of your report, but you're welcome to put figures in an appendix or put figures in the report itself. I personally like them when they are in the report itself, and if you're using LaTeX and, formatting things nicely with VSpace, and everything, you should be able to fit a nice, concise report with the figures in it in 4 pages. But again, part of this is that we start off in mini project 1 with pretty strict guidelines. The next mini projects will be more open-ended, and the final project will be very open-ended in an 8-page report. So it's supposed to be like a write-up you'd write when you're submitting to a workshop or to a conference, but a kind of mini version of that. I think that the code, yes, so it's nice. So the code should have everything, your working implementations of gradient descent, your pre-processing, how you extracted the features. If you want to be super nice to us, the code could run and output, nice precise results that you have in your report. That's not required. The code is there for us to, like, we're not going to grade the style of your code, but if your gradient descent obviously wasn't working, we're going to take a peek at your code and try to figure out why. We're going to run plagiarism checks on your code. Your code is like the appendix. That's probably the best way to think about it. It has to be there. We're going to check that you submitted it, that it looks like a real implementation of gradient descent and your results make sense. But we're not going to say, like, oh, hey, I didn't like the fact that you did this while loop in that style, or that you output things in this way. Yeah. All right, cool. So getting to the content for today, we're going to quickly recall what we talked about at the end of our last lecture. And that was this concept of inductive bias and this bias variance trade-off that I think most of us are familiar with if we've been writing the quizzes this week. And we'll recall this idea that I made this statement that statistical bias in terms of this bias variance trade-off isn't necessarily a bad thing in machine learning. Again, in machine learning, in some sense, it's all about coming up with the right kind of inductive bias. And again, the right way to think about inductive bias is we're trying to come up with the right sorts of assumptions that we can bake into our model so that we can do well and not overfit. And I've listed here this optional reading, which is an interesting paper by Tom Mitchell at CMU. So what kinds of inductive biases have we seen so far? Well, we've talked about linear regression and linear classification. And so frankly, so far we've been talking about models that make linear assumptions. So in linear regression, we're assuming that there's a linear relationship between the input features and our output target. In linear classification, we're presuming that there's a linear hyperplane that's separating the different classes. And we can also think about the kind of generative assumptions. So we talked about these generative models for linear classification and these interpretations of linear regression in terms of likelihood. And here, when we're talking about generative assumptions in the linear regression case, really this mean squared error linear model falls out of some simple Gaussian normality assumptions on our errors. In linear classification, we talked about some different generative assumptions. We talked about the linear discriminant analysis, where we were making this assumption that all the features had a multivariate Gaussian distribution conditioned on the class with a shared covariance matrix. And then QDA didn't share covariance matrices. And then naive Bayes made these independence assumptions. So all of these different assumptions behind these models are kind of different forms of inductive bias. And I think something I've been hinting at so far is that linear models work surprisingly well, but there are many problems that require more complicated models and more sophisticated inductive biases. So now that we've covered the basic ground of linear classification and linear regression, and I will reiterate that these are really the foundation of all of machine learning and really critical and will keep coming up throughout the course. But we're going to now talk about what we can do that's a bit more sophisticated. And so moving beyond linear models, we're going to think about this mainly in terms of classification now. And in general, the course is going to take a bit of a shift. Mostly we're going to be talking about classification, with occasionally coming back to regression. But now we're going to think about having some sort of richer way of partitioning our data. So thinking about the kind of classification boundaries that we're drawing for classification. Previously, we'd always just been thinking of cases where all we had was some single linear hyperplane. But what if we want a richer partitioning of the space? What if we want to break the space up in a bunch of different ways? Or what if we want to break it up in a hierarchical fashion? And that's what we're going to talk about today, and we're going to talk about a model called decision trees that ends up in exactly these kinds of partitionings, and that can be viewed in this hierarchical fashion. So coming back to an example that we've used a few times now, I'm going to discuss the challenge of doing cancer outcome prediction. So this is a data set that we've used in a few slides, but I'll just reiterate it for us. So this is a data set where researchers are trying to predict the outcome of whether or not a tumor is going to recur. And there's a whole bunch of features, a bunch of attributes we have related to the radius, the texture of the tumor, and a bunch of statistics like the mean, the standard error, etc. And I'm summarizing a few of these here in kind of a toy way. Now, in a decision tree is actually a pretty intuitive model. So a decision tree is a model where when we're trying to classify whether or not we think that this tumor is going to recur or not, we're going to think about this as a sequence of decisions where first thing we do, so say we're trying to classify, there's one point, the first thing we're going to do is we're going to say, well, is the radius of this tumor, say, greater than 17.5? If so, let's take this branch. Now we say, is the texture have a numeric value greater than 21.5? If so, we go left. Otherwise, we go right. And each of these nodes in this decision tree represents a partitioning of the input space. So it's a way that splits the data. And we call these nodes kind of tests. So the idea is that at the very beginning, we're testing, we're saying, is the radius of this tumor greater than 17.5? And the idea is that once we get down to a leaf node, in these leaf nodes we have all of the training examples that satisfied all of the conditions along that branch. So if we have ones that have a radius greater than 17.5, and the texture greater than 21.5, we end up down here. In our training set, there's 33 examples where there was a recurrence of the tumor, and 5 examples where there was no recurrence. So how do we use these decision trees to actually make a classification? Well, it's pretty straightforward, and in fact, decision trees are, in a lot of ways, a bit easier to wrap your head around than something like linear discriminant analysis. So say we get a new instance where we have a radius of 18 and a texture of 12. Well, we just say, okay, the radius is greater than 17. The texture is not greater than 21, so we go down here. And now we end up with there being 12 recurrence and 31 no recurrence. Well, one thing we could say is we could just say, well, most of these are no recurrence. So let's predict no recurrence. So we just predict whatever the majority label at each leaf is. The other thing we could say is that there is a 31 divided by 31 plus 12 probability that this results in a recurrence. So basically all we're doing is that we're taking our training data, we're somehow using that data, and that's what we're going to talk about today is how we actually build these things, but we're somehow using that data to come up with this decision tree. It's a sequence of binary decisions. Sometimes they can be non-binary, but usually they're going to be binary decision trees, where this takes us down to a leaf. We get to the leaf and we say, okay, most of the time when we saw all of these properties, we didn't see recurrence, or we did see recurrence. And an important thing to note is that you can always convert a decision tree into a sequence or an equivalent set of if-then rules. So basically there's a way to kind of unpack this tree into a bunch of rules where we could say, if the radius is greater than 17.5 and texture is greater than 21.5, then the most likely class is that it's going to recur, and so on and so forth. And again, we can always calculate this estimated probability as well. Yep. Yes, so the challenge here is that obviously once we're given this tree, we're good to go. And you could kind of expert construct this tree if you wanted. And in some sense, decision trees are a very natural machine learning model because kind of implicitly this is what a lot of experts do, right? They don't explicitly maybe write down this decision tree or this set of rules, but a doctor is going to say, like, usually when I see this sort of situation as well as this sort of situation, usually this is the outcome. So the challenge here is that obviously things are nice and easy once we're given this tree, but it's going to be learning this tree that is the challenge. And in particular, what we're trying to figure out is what these tests are. So what are the kind of if-then tests that we want to run? So usually with these tests, and almost always, there's a few kind of simplifying things we'll do. So one thing is that each one of these tests, so one of these internal decision nodes, is generally going to depend on just one feature. So whenever we're kind of making a branch, we're going to say, just look at texture, and just look at the radius, just looking at one feature. If it's a discrete feature, then usually the simple thing you can do is you can say, like, does it equal this value or not? So discrete features are pretty easy to deal with. For real valued features, we need a threshold. So again, we're thresholding on is the radius greater than 17.5. You could say, or is the grade of the tumor in this set? Blah, 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 right? There's a whole bunch of different things you can do, and the challenge is how do we choose what these tests are? So learning in the context of decision trees is choosing a set of tests to make up our tree, as well as the shape of the tree, because we don't know, like, why is this tree only depth 2? I mean, we still have 33 recurrence and 5 and 12 and 31. Like, presumably we could add some more decisions and make things more pure, right? So the challenge with decision trees is making these decisions, deciding what are we testing on, how many tests are we running. And again, the intuition behind decision trees, kind of from a visual perspective, is that the tests that we have here are partitioning the input space. So what we end up with decision trees formally is a bunch of axis-aligned partitions of the space, right? These are axis-aligned, basically. All of our partitions are always at 90 degree, like they're always at these right angles to each other. But we can make these as refined as we want. But at the end of the day, in a standard decision tree, what we end up with is a nice kind of hierarchical partitioning of the input space. And so very briefly, before we actually get into the learning of decision trees, it's worthwhile to think about how expressive they are. Because at the start of this lecture we said, let's go beyond linear models. Let's use something a bit more interesting, something with a more rich inductive bias. But how much have we gained? What sorts of functions can we now represent now that we're using decision trees? So what kind of function can we encode? Well, one nice thing, in a way, is that every Boolean function, so every function on binary 1-0 inputs that outputs true or false, can be perfectly represented by a decision tree. This isn't that surprising because basically it's what a decision tree is. It's a sequence. A binary decision tree is a sequence of binary decisions, and if you take your truth table for whatever Boolean function you have, you can very easily encode that with your binary decision tree by having every entry in your truth table correspond to a path in the decision tree. So this is a pretty good thing, actually. It's because Boolean functions, again, once we've turned our real value data into thresholded decisions, we can represent any Boolean function. With linear models, we couldn't do that. So we've gained some interesting expressiveness. Again, decision trees are very different from linear models, so it's a bit hard to do a kind of apples-to-apples comparison. But it's also worth mentioning that some things are really hard to represent with decision trees. So in particular, something like a parity function. So we return 1 if and only if an even number of the inputs are 1. If we have m inputs, it takes 2 to the m nodes in our decision tree to represent that function. So this means that like the parity function is not that complicated, but using a using a decision tree, it has to be kind of an exponentially big tree to handle that. Similarly, a majority function is really hard to represent. So these are kind of artificial examples, but oftentimes the thing we'll do in machine learning when we come up with a model, some new kind of inductive bias, we'll say to ourselves, like, what are the adversarial worst case sorts of inputs that would break this thing? And so in the case of decision trees, they're not very good for some of these functions, but it's not very often that the thing we're trying to learn in machine learning is just a parity function. So again, the positive thing here is that we can represent every Boolean function, and many other functions can be approximated by Booleans. And again, in terms of kind of visual intuition, they're really good at problems where the class label is constant in axis orthogonal regions of the input space, where what that means is just if we have a data set where we can partition the different classes into boxes like this, decision trees are very good. And again, if we're in higher dimensional space, these will be cubes in a 3-dimensional space, hypercubes in an n-dimensional space. But what's nice is that unlike linear models where we had just one split, for decision trees, we can have a bunch of different splits. So you could have, this could be class 2, and all around it could be class 1, or this could be class 1, and this could be class 1. So there's a lot more flexibility for the class labels to change in kind of non-linear, interesting ways when we're using decision trees. Any questions at this point? Yeah. Yeah, so I've been saying hierarchical. Why have I been saying that? Well, it's because in reality, at the end of the day, we end up with a non-hierarchical splitting. But again, you might end up with a case that our decisions are hierarchical. So in fact, like it might be the case that in fact, in this example, I believe, if I remember correctly, like A and B, like this is these two are, where is it? I guess sorry, my clicker gets stuck like this. Well, we won't go back to it, but by hierarchical, what I mean is just that when we make the first decision in the decision tree, this splits the space in 2. And then we're splitting the space, you know, into 4s and so on. And so if you want to be, say, really efficient, you might not want to always go all the way down to the leaf. You might say, well, if I just make 2 decisions, then my model has pretty reasonable accuracy. And so there's this kind of hierarchical notion that you can get more and more and more refined decisions. These partitions get smaller and smaller and smaller. But you can also kind of look at your decision tree at the coarser level, so depending how deep in the tree you go. Yeah. Yeah. Well, that's a great question. So the question is this fact that at each test we're generally only going to look at one feature, does that amount to the kind of independence assumption that we saw, say, with naive Bayes? In fact, it doesn't, because there is a dependency here where so we split on this feature, but then the tests that we do later on, So say we split on the radius feature, but in fact, things that have really high radius tend to also have, various different textures, right? Then we're going to end up with very different distributions in the two sides, and that's going to influence the type of tests we make on those sides. Great question. Yes, this is another great point. So the point here is that, does this really need to be axis orthogonal? Do we really need to do binary decisions? Like, presumably we're just kind of making partitions here. They could be really rich, complicated functions we're using to partition the space at each of the nodes in the decision tree. Yes, that is true, but there's no efficient learning algorithms for those types of complicated, that I know of, for those types of complicated decision trees. It's possible that this is an area where there is recent research, but generally we stick to these binary decisions using a single feature at each internal node because we can guarantee that we'll be able to learn quickly under those assumptions. But it's in general, decision trees can be crazy. So. Yes. If my we'll go there. Oh. Okay. Yes, so by a parity function here, so what I mean is that, so suppose our features are just binary, and the true function that we want to learn is a function where the output should be 1 if there's an even number of 1s and 0 otherwise in our feature vector. Now, to encode that function, so it's a pretty simple function in some sense. Like if you were encoding that in Python, it would be one line of code. But in a decision tree, what you'd have to do is you'd have to say, all you can ever do in these binary decision trees is say, is this feature 1 or 0? So you'd say at the root, you'd start with feature 1, you'd say, is that one 1 or 0? And then the next decision you have to say, well, is that one 1 or 0? And the issue is that testing whether or not there's an even number of 1s just requires like representing every single possible input as a different branch in the tree. Like basically your tree has to have, if there's m binary inputs, you have to have a tree that is depth m, like a full binary tree to represent it. If that makes sense, yeah. Yes, and, well, yes and no. So yes, in that once we get to clustering, which is when we move off supervised learning and start discussing unsupervised learning, a number of clustering algorithms called hierarchical clustering algorithms are inferring trees. They can be interpreted as clustering the data, but again, we don't call these clustering algorithms because they're supervised. We're given a label, right? So we're clustering the space, but we're trying to cluster the space given that we know the class labels and all the data points. Whereas when we talk about clustering in machine learning, that's usually the setting where we don't know labels for any of the points. So we're implicitly getting a clustering of the space. Same as for linear regression. We were splitting the space into 2 clusters. But we don't call these clustering because our goal is that we know already that we have a training set of 1s and 0s, and we're trying to find the best split to match that clustering we're already given. Whereas when we talk about clustering approaches for machine learning, that's usually when we're not given any labels and we're trying to find a good split. Great question. Yep. It's a great question. So the question is, how do we choose, which feature we split on first at the root node? So it can be any of the features, and that's a good segue to, we're going to choose which feature and what the split should be actually using information theory. So that's where we'll get to now, which is how we actually learn these things. So how do we choose which test to do at which point? Yep. It's a fair point. Yes, but if you did so, but that would be changing your input in some sense. But yes, so you could get around this by, that's why it's kind of an adversarial example. But it's a fair point, though. Yes, if you introduced a feature that was just a bit that said, is there an even number of ones, then you'd only have a depth 1 tree and you get 100%. So, fair point. Yeah. Okay, so, oh, yes, one more. Yeah, so this relates, so the question here is, do the decisions at each point, in a sense, have to be linear? In fact, here they're even simpler than linear. They have to be like just a threshold or like a very simple. And in principle, no. But to facilitate tractable learning, yes. So you could come up with a crazy decision tree algorithm where you allowed extremely complicated functions as the decision at each node, but it would be kind of computationally impossible to learn that thing. And that, brings up exactly this here, which is how do we learn it? And that's, first off, the simplest thing you could think of is, okay, let's assume we have a finite number of features and a finite number of possible tests we could do, right? Well, why don't we just enumerate all possible trees, see which one does best on the validation set, and call it a day. Would be reasonable, but you're going to have to remember that we have a bunch of, in the worst, even the simplest case, binary decisions. This is still going to be a huge exponential set in the number of features that we have. So even if we're just making a binary decision at each of our m features, we'd have to search over a space of 2 to the m possible trees. And this is a huge search space, and we're probably going to end up overfitting if we're doing this. So that's not the reasonable thing to do. So how do we actually learn them? The approach that we use to learn decision trees is, it's often called the top-down approach, or this kind of recursive approach, where what we do is first we figure out, okay, given my data I have right now, what is the best split I could do that would be the most informative? Now I split my data, that's the first branch in the tree. And now I've done this first split, I then look at this data set and I say, okay, now this data set that is on the left side, I want to split that data set the best way I can. And you kind of recursively do it. So it's really, at every point in time, we're just trying to make a decision, which is, given the current number of points, or the current set of points I have in my branch, what is the best decision I can make? So formally, the algorithm here is that given a labeled set of training instances, the first thing I do is I check, do all these training instances have the same class? If they have the same class, I create a leaf with that label, and I call it a day. Oh, one thing I should say is that we also talk about at the end that we generally do something called pruning to avoid overfitting. So that's an important thing to come back to. But yes, our algorithm in the simple case is I say, okay, I look at the set of instances I have now that I'm at kind of this point in the tree, and I say, are these all the same class? If they are, great. I make a leaf, I'm done. Otherwise, I say, okay, I have to pick the best split, the best test from all my features and all the possible thresholds, and I say this is the best test, the most informative way to split the data. Now I split the data according to those steps, or according to that test. Now I end up with 2 labeled data sets, and then I recurse this whole process. And really, all of the work of this entire learning algorithm is in step 2, which is picking the best test. So what makes a good test? So the test ideally should be really informative. Ideally, we want to choose tests so that once I test whether or not, say, the radius of the tumor is greater than 21.5, that gives me a maximal amount of information about whether or not this tumor is going to recur or not. That's kind of the intuitive thing here. And if you can think about 2 example tests here, so one on the left, we have a test where at the end we split it into a data set where we have 20 positive and 10 negative on the true side, and 10 positive and 0 negative on the right side. And then on the other example, we get 15 and 7 and 15 and 3. Now it kind of feels like this one on the left is maybe a better thing to do, because if we do this test, well then we guarantee we know it's a positive on this side. We have a perfectly pure leaf with this test, which is a reasonable intuition, but the question is, how do we actually formalize this? And the challenge, again, is that we want to formalize this mathematically, this idea of maximizing the amount of information that we get from a test. Which brings us into a brief foray into information theory. We're not going to do a whole course on information theory, but it's important to understand the mathematical notion of information, because that's what we're going to use to make this decision. So to get our intuition for information theory in this context, we're going to consider a pretty simple situation, or three different situations. In the first one, you're about to observe a dice roll, so a simple six-sided die. Another situation where you're going to observe the outcome of a coin flip. And another situation where you're going to observe the outcome of a biased coin flip. So say this coin 75% of the time comes up heads. Now, in each of these situations, you have a different amount of uncertainty about what the outcome is going to be. So when you're observing a dice roll, there's 6 possible things that could happen with equal probability. A coin flip, there's 2 things that could happen. A biased coin flip, there's 2 things that could happen, but you know that heads is more likely. So information content is really all about how much reduction in uncertainty there is after you see the outcome of one of these events. So intuitively, when someone says, I rolled the dice and it came up 6, that's more surprising, that's more informative than someone saying, I flipped a coin and it came up heads. Because there was 6 possible things that could have happened with the dice roll, but only 2 possible things that could have happened with the coin flip. And so formally, what does this information content look like? Well, let's say that we have a sample space of events, E, and then each of these events occurs with a probability PE. Now, if we're told that event E happened, so event E might be us seeing a 1 on this dice roll. If someone says, I saw a 1, well, the information content of that event, the number of bits of information we get, is the log base 2 of 1 over the probability of that event. So you can think of this intuitively as the amount of surprise that we got, that there was in this event. So kind of useful case to think about is that if the probability of this event was 1, if I had a dice that just had 1s on all sides, and I said, look, I rolled a 1, you'd say, well, of course you rolled a 1. There's only one thing that could have happened. So there's no information in that event. If we knew it was going to happen and someone says it happened, you're like, okay, it happened. There's nothing interesting, but the more uncertainty there was prior to the event happening, the more surprising it was, so the more information we got from that event. So mathematically, we get 1 bit of information from a coin flip, and again, this is intuitive because there's 2 things that could have happened. It could be a head or a tail, it could be a 1 or a 0. We saw one of those things happened. It takes 1 bit of information to transmit the event to us, to transmit to kind of correspond to that amount of uncertainty reduction. The dice roll, on the other hand, has about 2.58 bits of information. And so when we use log base 2, these are bits. If it was log base n, they'd be called nats. So these are units of information. And this was just the information here of 1 event. So this is saying, look, I saw a 1 come up in the dice roll, or I saw snake eyes. How informative was that? But something that we care about a bit more is the entropy, which is not the amount of information in an event that happened, but how much information there is in a distribution of events that could happen. So again, this distinguishing between this idea of a dice roll versus a coin flip. And so entropy, we usually talk of in terms of an information source or a probability distribution. So presume we have some information source S that emits symbols from some alphabet. So you can think of this being, there's a bunch of events that could happen, S1 up to SK. And each of these events has a different probability of happening, P1 to PK. And we know these things. So we know that, in general, is an unbiased coin or it's not a biased coin, etc. Now, we're also going to assume as we often assume in this course, that every time this information source emits a symbol, it's independent from the other emissions. So we're often making these independence assumptions. We're making another one of these here. So what is kind of the amount of information, the amount of uncertainty in this information source? This is what's called the entropy. So the entropy of this information source S is going to be equal to us summing over the alphabet, so all the possible things we could see, taking the product of the probability of each of these possible events times the information content of that event. So if we're thinking about things in terms of probability, what we're looking at here is the expected amount of information we get by observing the outcome of this information source S. Right? We're summing over all the possible things that could happen, all the symbols in our alphabet, multiplying by the probability of each of these events times the information content. So this is the expected information content from this information source. And generally, this only actually depends on the probability distribution. Doesn't need to be a symbol or an information source outputting symbols. Any probability distribution with a bunch of different events, we can say, what is the entropy of that probability distribution? For discrete here. We're going to focus on discrete for this entire course, or for this entire lecture. So there's several different ways to think about entropy. You can think of this being kind of, the expected amount of information, the average amount of information per symbol, the average amount of surprise you get, the uncertainty there is before we see the outcome. So again, there's more entropy in a dice roll than there is in a biased coin flip. And somewhat of, I think, the most formal way of thinking about this is the average number of bits you need to communicate what actually happened. So if we're looking at binary classification, so suppose we're trying to classify sample data using a decision tree. We have p positive and n negative examples. We can compute the entropy of this data set, right? So if we have a really high entropy data set, that means it's pretty hard, because if we have maximum entropy, this means that it's a 50-50 shot of whether or not this thing is true or positive, or true or negative, right? Whereas we can calculate formally this given here. Again, there's only two possible events here. It's either positive or negative, it's true or false. So we can just compute this entropy equation we had here. Now we're summing over just the two possible events. So is our training example true or false? And the entropy of our data set is how much uncertainty we have. If we had zero entropy, then our data set would be all ones or all zeros, and we'd be done. We wouldn't need to make any prediction. So coming back to our example here, well, one thing we can compute is, well, first off, let's just say, what is the entropy of this data set? This gives us a sense of, okay, at this point, we have 20 plus 10, 30 positive examples, 10 negative examples. How much entropy is there? How hard is this? Now we have this kind of baseline, how difficult, how much uncertainty we have. But this still doesn't tell us how we're actually going to choose which of these two is better. And to do that, we need the notion of conditional entropy. Now, conditional entropy is pretty straightforward based on entropy, but this is the entropy of a variable conditioned on another variable. So, in particular, the conditional entropy of y given x is we're summing over the possible values for x and then computing the entropy of y given those values. So this is basically saying to us, how much does knowing x change the uncertainty in our variable y? And this is a really important thing to know, because suppose the conditional entropy of y given x was 0. Well, then if we know x, we know y. Then if the conditional entropy, if given x, y is totally determined, then we have a conditional entropy of 0, and things are great. And so in particular, when we're trying to choose which test to look at here, we can say, well, the entropy of the data set to begin with was this much, but conditioned on the outcome of test 1, the entropy of this choice is 0.688, and conditioned on the outcome of test 2, the entropy is 0.788. So these two tests change the amount of uncertainty we have in this data set. And this tells us how to choose which test to use. Because what we want to choose is we want to choose the test that gives us the most information gain. So we want to choose the test that has the lowest conditional entropy. Again, if our conditional entropy, if given that we test whether or not the radius is greater than, say, 0.5, and we have all ones on one side and all zeros on the other side, well then we know completely there's no uncertainty left in our data set. So what we want to do is we want to find tests that minimize the conditional entropy, and we often call this the information gain, because we have the entropy of our entire data set and subtracting the reduction in uncertainty given our test, and we want this to be maximized. Again, in the best case, the information gain is going to give us all the information about the data set. Okay. So, how do we choose the best test? How do we actually build our decision tree? Well, what we do is we do this recursive algorithm. Every time we say, okay, there's 1,000 possible tests we could run. We have some bank of possible tests. It's like, oh, we could test whether or not the radius is greater than this. We could test whether or not the size is this, so on and so forth. For all of these different tests, we compute the information gain, and we choose the test with the highest information gain. So this seems well and good, and in fact, it's not that complicated of a computation. So these conditional entropy computations, so I'm not going over all the details here, but this is really just taking a bunch of probabilities, so similar to, so here, just taking how many trues and falses do I have if I had taken this branch times the log of that. It's just pretty simple kind of division and then logarithms. But one of the challenges here is that this tells us how to come up with the best tests, given that we have all the set of candidate tests we might try. But things can get a little funky with certain types of tests. And in particular, one thing is that so far I've been assuming we're making binary decisions, and that's kind of a necessary thing to do, because if the outcome of a test is not binary, then the number of possible values influences the information gain. So it's kind of comparing apples and oranges. If you're saying, how much entropy reduction would I get if I did a test that has 10 possible outcomes versus a test that has 2 possible outcomes? It's kind of an unfair comparison, and so generally we like to stick to binary tests for that reason. Another thing is that, again, sometimes we'll have attributes that are not just binary, but real valued attributes or discrete attributes, so we have to find some way to transform all of these into binary decisions. So if we have k possible values for some attribute, then we have k possible binary decisions. And the most popular, so the standard way that people learn decision trees is we always just look at 2 possible types of tests, of decisions. One is that for discrete, so if we have attributes like the color of the tumor, our tests are all tests of the form, is the color equal to X? Is the color equal to Y? Is the color equal to Z? So if there's 10 possible values for some feature, then there's 10 possible tests that come out of that feature. And then for continuous features, all of our tests are just these simple thresholds, where we say, is the attribute less than a value? And this is what's called, bizarrely, the C4.5 learning algorithm, but this is the standard learning algorithm for decision trees, is basically using this information gain idea. So how much reduction in uncertainty do we get? And when we're trying to choose the tests, we look at all possible tests that are of this form. And of course, there's the caveat of how do we actually choose the real valued features that we're using. So it's obvious that if we have a discrete feature, well, there's only discrete feature with k possible values, there's k tests. A binary feature, there's 2 tests. Is it true or is it false? So a real valued feature, in principle, there's an infinite number of thresholds we could try, and we don't want to try all infinity of these possible different tests. So in practice, what we do, there's two options here. So one is you can choose the midpoints of all the observed data values. So say if in our training set we have all these triangles here, then when we're saying, well, what are possible thresholds we could use for this feature, we just choose the midpoints of all these data points as our possible threshold values. Another slightly more sophisticated, in some sense slightly better approach is not just taking the midpoints of all of our observed datas, or all of our observed points, but the midpoints of the data values that have different classes. Sorry, actually, oh yeah, different y values, yes. So we would say, oh look, when things were on this side, they were no recurrence. Over here, they were recurrence. So that's probably a good place to do a split here. A midpoint between two data points that have different classes. And same as here. So this is reasonable because why would we split the data right here when we know that on both sides of this threshold, this is a no recurrence? Again, you might wonder that maybe in the test data there is a recurrence here. But in general, this approach usually works better, and it's what's used in the C4.5 algorithm. Okay, so that's how we construct our decision trees. It's no, you would try all of these. So again, this computation of the information gain is really not that expensive. So you can afford to try like 10,000 tests, right? I mean, that's maybe a bit much, but you don't need to be really stingy in how many tests you're trying because all the computation is, like again, to get the information gain for our example there, I was able to write down the entire computation on the bottom of the slide. Like, this is what we need to compute. That's extremely fast to compute in a computer. We can compute that 10,000 times. It's not a big deal. So generally, you don't want to... You want to make sure you're doing enough tests. Again, the reason why we'd want to split on the midpoint of the ones with different classes is just because it seems a bit wasteful and just probably not going to do any... I mean, frankly, it's not going to do anything good if we're splitting in between here. There's very rare cases when that's actually going to be the highest information gain test. But yes, I think decision trees, they're one of the older kind of classic machine learning methods. And so, a lot of these initial things were, devised when computers weren't as fast as they were now. But you don't need to worry too much. You can try a whole bunch of different tests. You could even try random threshold values if you wanted. It's probably not going to make a difference, but... This is a great question. We'll come back to that. So I'll say in the simple algorithm that I described, we'll come back to it, but in the simple algorithm, you keep going until you have zero entropy. So until you have all of the labels in this portion are the same. That is in the kind of first step. You keep growing until you get to there. Or you might have some entropy threshold, but usually that's zero. Then afterwards, you're generally going to kind of prune things back a little bit because you can overfit if you're growing everything to purity. So we'll talk about that in just 1 second, but one quick thing I do want to mention is that decision trees can be used for regression. So I was talking about classification here, and that's where all this fun with information gain comes with. But we can use decision trees to also predict real valued outputs. So say we weren't trying to predict outcome, but instead we're trying to predict the size change. Well, what we would do is we'd have our same decision tree, but in the past, this was how many recurrence and how many non-recurrence we had at this leaf. Now we're just going to have the set of all the size changes we saw in this kind of, once we've made these partitions of the data. And then when we're trying to actually predict, given a new data point with a radius of 18 and a texture of 12, what do we predict for the size change? Well, again, we follow the decision tree until we get to the leaf, and then we just predict the mean value we have for all the training examples at that leaf. So how do we actually train these things in the regression sense? The regression case is a lot easier. all we do is the exact same thing that we were doing before, but now we don't worry about information gain or anything. All we say is which test gives us a lower mean squared error, and we use that test. So you can do this for classification or regression. They're much more popular for classification, but you can do it for regression. It's a reasonable baseline algorithm. And again, you don't need to do information gain when we're doing regression because, well, that gets a bit more complicated because we have a continuous output. But we just use which test gives us the lowest mean squared error. So just to give a quick artificial example, so this is a data set that was generated, and what would it look if we ran so we ran this full decision tree algorithm to classify the red versus the blue, and we again ran this until every single leaf gives us 0 entropy. So we have complete every leaf in the tree, every partition in this plot is just one class. And you can see there's some kind of funny things, like we have to get pretty precise here to have these two be in a different class than this blue one, than this red one, right? So we're ending up with some pretty little boxes, so some pretty fine-grained decisions, some pretty deep branches of our tree to be able to tell these little parts apart. And of course, how we assess performance of this, is we're training our model, we're figuring out the best tests on our training set. So when we're choosing which test has the most information gain, yep. This is a great question. So the question is, well, how do we handle the case when multiple data values have the same input but different outputs? Well, this is actually, this doesn't just happen for decision trees, this happens generally. And frankly, those are going to have minimal impact on your learning because they're kind of not pushing you in either direction, right? So in some sense, they're just kind of uninformative data points. You could almost just throw them away. It's exceedingly rare because, again, if you have real valued features, the probability of that happening is 0. And if you do see that, it's maybe a reason to double check there wasn't a pre-processing error. It's a great question, though. But yeah, so again, when we're figuring out which tests have the highest information gain or which tests have the best mean squared error, we're choosing what are all the tests going to be. We're splitting our data. We're doing this on the training set. But then we're going to evaluate our performance on a validation set. And what you're going to see if you run this algorithm where we're getting every leaf having totally pure, every leaf just has all class 1 or all class 0, you're probably going to notice that the method overfits a ton. So here, this is the training accuracy, and then this is the validation accuracy. And you can see that this is the size of the tree. So this is how many tests we have, how many nodes are in the tree. Apologies, it's hard to read. But you can see that after we make the tree, even just maybe 10 nodes, our training accuracy keeps going up, but our validation accuracy is going down. So as the tree grows, we can get better and better at fitting the training data, but that doesn't necessarily make us better at generalization. And coming back to this example here, again, once we got to the point where we're making these little splits to tell apart this blue one from these red ones here, it's really hard to say if that's actually kind of a generally useful thing or if this blue point here is maybe just a weird point. Like maybe we shouldn't be tweaking our tree to accommodate this one little point here. So in practice, what we do to actually avoid this overfitting problem is that we're going to remove some nodes from the tree. We're going to get rid of some branches to avoid overfitting. And there's 2 ways to do this. One is early stopping, which is basically we just say, okay, let's stop adding more tests to the tree. Let's stop this recursive tree growing process once it looks like our error on the validation set's going down. And another, perhaps more popular approach is called post-pruning. So we're going to grow a full tree, and then we're going to eliminate nodes that have the lowest information gain on the validation set. So in general, post-pruning is better, and there's a mathematical reason for this. And it allows you to deal with cases where a single attribute isn't very informative, but a combination of attributes is informative. So what we mean by this is that there can be strange cases where it looks like you're not doing any better on the validation set by adding this test. But if you added this test and then another test, that would allow you to get a big gain on the validation set. This is because of the fact that the features might not actually be independent, and each of our tests just considers one feature. So in general, the best thing to do is to actually grow a complete tree where we get down to information, or kind of zero information, zero entropy at all of our leaves, and then we kind of look at our tree and we prune away things that don't give us a big gain on the validation set. One second. Oh, there we go. Yes, and so formally, how this works is there's different approaches to it. This is the reduced error pruning, aka post-pruning. So we have our validation set. We grow our big tree. Now for each node, we're going to evaluate the validation set accuracy of pruning, like how good do we do with the full tree versus with a tree where we've removed this node and all the decisions beneath it. And then we greedily get rid of nodes that give us the best gain, that lead to the highest validation increase. And then at each of these points, we're basically just, if we got rid of this node, well, we're just going to, again, replace this by a leaf. And we stop pruning when our accuracy gets worse on the validation set. And so what this looks like here is that, again, this is our training error as we grow a really big tree. And here's our validation error. It goes way down here. But then if we prune, we shoot back to this point here. So after pruning, we're still not quite as good as on the training set. And in fact, we would have maybe done a little bit better if we would have just stopped even at this point. But with this post-pruning, we end up doing pretty close to the best we could have done. So what are the advantages of decision trees? Oh, yep. This is a great question. So how do you avoid overfitting on the validation set? This is probably one of the places where you're most prone to overfitting on the validation set, because we're kind of using our validation set almost to train in this sense. Like, you can think of this post-pruning as like a hyperparameter, like the learning rate, or some other, like, which features to use. I would say this is definitely a place when you're using these decision tree algorithms, A, because they're very fast, and B, because of this risk, you should do cross-validation. So you shouldn't just keep using the same validation set. You should probably do a bunch of random validation sets and make sure that you're not overfitting too much. So what you can do, for example, is you can take your training data, or training data plus validation data, and do 10-fold cross-validation, where each of those 10 folds, you grow a decision tree, use the validation set to prune it, and then at the end of the day, you get 10 different trees, and then you can output the majority vote of those 10 different trees. It's a good way to avoid overfitting. Any other questions? Yeah. Yes. So every time it's worthwhile to consider every possible test, again, because their features might not be independent. So say there's 3 features in your data set, and so one of these is binary, one of them is continuous, and one of them is discrete categorical, and you have 50 possible thresholds for the continuous one. You have 2 decisions for the binary one, and say there's k classes. So at the end of the day, you have 50 plus 2 plus 3, so like 55 possible tests you could make. Every depth of the tree, you're going to consider all of those possible tests. Because again, obviously, if you just tested on doing is radius greater than 15, you wouldn't choose that again at the next level. But the thing is that it might make sense to do is radius greater than 15, and then is color blue, and then is radius greater than 15 again, might still be useful. Again, because the features might be interacting with one another. Yeah. This is a really good question. So yes, there are ways to do this. We're going to discuss techniques for this in one of the upcoming lectures. It's a lecture. So to give you a quick preview, you can just test how correlated those features are. So using a correlation measure such as Spearman's correlation or the Pearson correlation, if they're continuous features. If they're not continuous features, you can compute something called the mutual information between them, and we'll talk about that. And that's a nice measure of how dependent they are from each other. And you might want to get rid of really correlated features in your data. It depends. So yeah, generally, if they're super dependent, you should probably recode them or get rid of one. For decision trees, it's not going to hurt you that bad. For linear regression, if you have extremely correlated features, that can mess up the numerical stability. It's not going to hurt you a ton to keep them in there, but generally you want your features to be independent, because then they're going to give kind of as independent as possible, or as kind of providing different information, because if they're just redundant, then you're wasting computation resources. Yep. Great question. So the question is, generally, is linear regression or decision trees better? Can't say in general. I would say that we're going to talk about some more advanced versions of decision trees, something that are called random forests, which are kind of related to this earlier question about how do we stop overfitting. We make a whole bunch of kind of random trees and we ensemble them together. Those are almost always better than linear models, but a straight up C4.5 versus linear regression, I'd say it's a toss-up. Yeah. Yes, indeed. So the output of a decision tree on a regression task is discrete in the sense that there's only, if you have 50 leaves in your tree, you only will output 50 different values. So it's kind of an interesting point. I would say that linear regression is probably better than decision trees for regression. For classification, it's more of a toss-up. And yes, so just, related to that, what are the advantages? One of the biggest advantages, so besides them being fast, the fact that they have a bit more of a richer space than linear models in some sense, is that they're really interpretable, right? If a domain expert says, why did your machine learning model make this decision? You're like, well, you can read off the if-then rule. We said, well, it had a radius greater than this, it had this color, and we saw that 85% of the training examples, that resulted in recurrence. So in terms of interpretability, which is an important part of machine learning, decision trees are pretty hard to beat. Limitations is that they can be pretty sensitive. So if your training data changes a little bit, your decision tree can change quite a bit, and that's kind of unfortunate. When you have lots of tests in your tree, some of them can kind of be weird, and you're like, why did I test on this being greater than 32.3, and then 2 branches down, tested on it being greater than 32.7. So it gets a little weird, and it has trouble with things with decision boundaries that are very curved as well. Although we can extend it to use nonlinear, but then it's hard to learn. So with that, we will call it. Good luck with the rest of Mini Project 1, and in terms of knowledge today, you should know all about decision trees, how to train them, why they're good, why they're not good, and how to detect overfitting and solve it. Yeah.
Today you just talked about the correlation matrix for calculating something. So let's suppose if you calculate correlation with of input feature with a target vector like.
Yeah, that's a good heuristic for whether or not it's going to be a good feature.
About the validation set. The validation set is actually like training set. Yeah, I mean that we should run this set on the algorithm and calculate the weights, and then
No, so you should only calculate your weights of your model on your training set,
okay,
and use your validation set to validate how well your model is doing.
it's like the test set,
It's like the
right?
test set. It's like the validation set's like the test set that you run on, that you use a whole bunch. So the validation set is just like the test set, but it's what you use during model development, and the test set is the thing you only look at the very end.
I see.
Yeah, so the validation set's just like the test set.
One more example.
Yeah.
Suppose that we run the algorithm on the test set when we add one feature
Yeah.
that we are not supposed to, but we run it.
Sure, yeah.
Is it possible that the closed form solution has a worse mean square than our gradient descent algorithm?
That's interesting. It's possible, but very surprising. I wouldn't expect that to like if it's a very small difference, that's reasonable. If it's a big difference, possibly a fortuitous bug in the code. Yeah. So I'm gonna walk towards